Thank you. I'm Christian. I'm a PhD student at EPFL. This is joint work with Lucy from Georgetown, Justinas and Vincent from the ICRC, that's the International Committee of the Red Cross, and Carmela from MPI and EPFL. So if you're not familiar, humanitarian aid distribution is a process where NGOs distribute physical aid or kind of cash, medicine, food to recipients. Historically, this has been a very manual process, so that might be slow, error-prone, and costly, and there's been a strong push in recent years to digitalize this process. Now, as you can imagine, digitalizing humanitarian action is very risky. There's a lot of very sensitive data. It's a very kind of unstable context. And so there's been a lot of work trying to build optimal privacy-preserving protocols to do aid distribution without learning anything that's needed beyond the thing that we need for aid distribution. Now, we went to the ICRC, and they were like, this is very nice. You know, you have all these pets, and we have optimal privacy, but sometimes we need to know if the distribution was successful, if it reached the right targets, if it doesn't discriminate. And we can't do that because we don't see anything about what's happening. So that's what we're doing in this work. We're trying to add assessments on top of a privacy-preserving aid distribution protocol. I'll show you the requirements. If you want to know how we go from like very fuzzy, high-level requirements to something that's more formal that we can start with, please come see me at my poster. I'm very excited to talk about that. But I'll just give you the requirements that we synthesized after a few months of iteration. So first of all, the setting. In aid distribution, recipients typically go once to a registration station. They sign up, and they get tokens in exchange. And then during a given distribution period, they can go and exchange those tokens for aid. And they can have multiple periods over a single distribution deployment. Typically, at the end of a distribution, there's an audit that's happening. So an external auditor will, for example, go check to see if the amount of physical aid that was distributed matches what has been reported. So we want to assess this process. What does it mean concretely? So we split those into two types of assessments. The first one are what we call simple assessments. These are questions like, what percentage of pregnant aid recipients were able to successfully claim aid in this distribution? And then we have more complex assessments. Things like, what is the contact information of all recipients that are above the age of 60 and also haven't been claiming aid in the last 3 periods? This is typically for duty of care, so you would kind of go and check on those people. And so these full assessments talk about people who didn't show up. They talk about information about multiple periods in the past. So that's our goal. In terms of the deployment requirements, this is kind of an unusual setting maybe for pets. The registration and distribution station have limited computing power, something like an old laptop, limited connectivity, maybe like a satellite connection from time to time. The recipients are very low-end devices, so maybe kind of a very old phone. Sometimes they don't have any compute at all, and they're issued a smart card, which has like a very tiny CPU on it by the ICRC, and we don't expect them to have any connection. So they will have to physically go to the station and kind of do some NFC protocol or Bluetooth to exchange information at all. And we need the system to be fast. So any minute that we spend here to do additional crypto or pets on top of just giving the physical aid over a counter is a minute that the distribution station and the recipient have to spend in this unstable situation, which might be a natural disaster or a ceasefire, and that puts the recipients and the staff at risk. So we need this to not slow down aid distribution. Finally, for the threat model, we assume recipients are honest for the purpose of assessments. We assume they're corrupted up to a threshold by the adversary. The registration station we model as honest but curious. This is typically a very kind of stable, one-time setup. And distribution might be either semi-honest or malicious, depending on the situation on the ground. All right. We want pretty typical guarantees for assessments. We want them to be unforgeable, so they have to accurately reflect what's going on the ground. And we want them to be private, so we want the output party to only learn the assessment and basically nothing else about recipients. Interestingly, we also had to come up with meta requirements, which are maybe a bit specific to the nature of humanitarian action, but I think they're also applicable in a lot of other contexts. And the first one is some kind of agility. So we deploy things with a given threat model in mind, but sometimes that threat model gets invalidated and changes, right? There's like an uprising or like an armed militia takes over your station, and now suddenly your adversary is much stronger than you expected it to be. And we could design protocols for this like very strong use case, but then we had to pay a price for it, usually efficiency. And in our case, being less efficient means putting people at risk because everything gets slower. So agility just tells us if we notice a threat model change, there's a way to relatively quickly either strengthen a protocol that we have deployed or to safely shut it down so that we can adapt to the threat model. conversely, we also want graceful degradation. So while, when threat model changes and before we've been able to use agility, we don't want the system to catastrophically collapse and just kind of leak everyone's information, for example. And to argue about this, we draft the raw protocols, and then we also derive the potential leakage and harms for all stronger threat models. And we argue that this is bound and acceptable. So those are the requirements. I'll just sketch how we built our system. A natural kind of primitive you would start from when you do any kind of assessment or statistics is functional encryption, which has a bunch of algorithms. You do some key generation for a function f. Here f would be the function that computes the assessment. And you'd send the secret key for f to the station and the public key to recipients. And recipients can then encrypt their information using the public key. And once you have a bunch of these ciphertexts, you can call an evaluation function using the secret key. And if your FE scheme is correct, you'll get back the assessment. Now, this has an obvious flaw, namely, the adversary is not constrained in how they can evaluate. Right? For example, they could pick a single ciphertext, evaluate the assessment, and learn much more than the assessment for the entire distribution, which is what we actually want to reveal. So the way we address this is we restrict the adaptivity of the adversary. We just allow it to query the function once. So we formalize this as a one-time functional encryption scheme. And it just says, yeah, you can get the evaluation, but only once. If you've already evaluated for a given, let's say, a period, you get nothing. This is inherently a stateful primitive, so you can't do it only with pure traditional crypto. You need like some quantum stuff or another party that helps you keep track of state. Here it looks like I'm pulling this helper out of thin air that didn't appear before. We have very good reasons to believe that this is something that we can actually deploy in practice. I'll just talk about it more in the poster. This is a very reasonable deployment setting for us. And the crypto you use is pretty standard. So lightweight, use public encryption signatures and either secret sharing or like some lightweight threshold of encryption. Okay, so that's the kind of semi-honest construction. We still have an issue here, namely the set of ciphertext that is evaluated. You can only evaluate once, but you can still pick which ciphertext. So you might learn, kind of maybe the wrong assessment, or you might still, for example, pick a single ciphertext and request that output. So for that, we'll use another mechanism. In fact, we'll rely on the auditor. So we're in the kind of pets in the physical world session. So we have an oracle that tells us what's happening in the physical world. So the mechanism that we're going to use is that the distribution station will pick the inputs it thinks it needs to evaluate, and it will send them to the auditor for certification. So the auditor will check, is the metadata that comes with these commitments actually consistent with what I'm seeing on the ground in this warehouse? And if yes, we'll issue a certificate. The recipients encrypt as before, and then now we want this predicate one-time functional encryption primitive to say you can only evaluate once, and only if the certificate on the inputs is correct. And this will kind of tie us back and bind us to the physical amount of aid. And again, we can use a helper, and we can use very standard crypto primitives as well. I'll just show you some efficiency numbers. The top two rows are for a simple function, which is how many pregnant recipients were able to claim aid. And the bottom one is this complicated reveal information of people over 60 that haven't claimed aid in the last 3 periods. I'll just draw your attention to the rows in yellow. These are the things that happen during distribution. So these are the things that we really care about that are critical to be very fast. The things in gray on the left are the completely private protocol and their overhead. So we kind of take the column on the left and we add one of the other columns. The takeaway is that you only ever send a few hundred bytes at most, and you'll spend 100 milliseconds at most on like a very low-end phone. So this is actually very, very practical. I have much more numbers and details on the poster. Thank you very much.